Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. What has tickled you in the world of science this week?
Well, I thought I'd talk about the volcano, really.
Oh,
it's, good. Seeing as it seems to be the major news story of the day. It's a volcano on Iceland. I mean, Iceland is basically the result of a giant volcano. Iceland is sitting in the middle of the Atlantic Ocean, and the Atlantic Ocean is slowly getting wider, a couple of centimetres a year. And there's a ridge down the middle where the two plates, the European plate and the American plate, are being pulled apart. It's a bit like if you've got a bowl of custard and you get a skin on the top. If you imagine a crack down that skin, and if you slowly pulled that crack apart, you get more warm custard coming up, and it slowly form a new skin, and it keeps pulling apart and it keeps forming new skin. So there's volcanoes all the way down the middle of the Atlantic Ridge. It's called the Mid-Atlantic Ridge. And then also on Iceland, you've got a really, really hot piece of the mantle. That's the layer below the crust. It's called a hotspot. Geologists are very imaginative with their names.
Yes.
And so you're getting extra volcanism there, and it's extra high, and that's the reason why it's out of the ground. So Iceland's basically just a big volcano. And there's a volcano under a ice cap called... everyone else seems to be giving up on this name. I'll give it a go. Eyjafjallajökull or something. Eyjafjallajökull.
Oh, we'll never get an Academy Award, will it? Let's face it.
I don't think my Icelandic's very good, I'm afraid. And so there's a volcano erupting under there.
Wow.
And because there's a great big ice cap on top of it, it's melting and producing huge amounts of hot water, which is flowing down in a river, and it's washed away one of the major highways in Iceland.
Gosh.
And it's also throwing up so much steam and ash up into the atmosphere, up 40,000 feet up into the atmosphere, and then that's getting blown down over the top of us. And that wouldn't be a major problem for us. We might get a bit of dust on the car if you're unlucky, but not very much. The problem with aeroplanes, because this dust is very abrasive, and if you fly a jet engine through it, it'll wear out the jet engines. And even if it isn't a major problem when you fly through it, although that can cause issues when you're actually flying through it, it's going to wear out the jet engines and cause millions of pounds worth of damage.
And so we start on the phones this evening for Dr. Dave. We've got Pat on the line from Lowestoft. Good evening, Pat.
Good evening, Sue. Good evening, everybody.
You're through to Dr. Dave.
Dr. Dave, now I appreciate the planes have been grounded because of safety.
Yeah.
Now these volcanoes are going off all the time, aren't they? And I can't remember all this bother before.
It basically just depends on the eruption. There's volcanoes going off all the time all around the world, and there's lots of planes having to be diverted by volcanic ash in the world. It happens every month or two if you get a big eruption. But very rarely is there a volcanic eruption which affects the UK because there aren't many volcanoes nearby. The nearest ones are on Iceland. And so you need to have a big eruption on Iceland and the wind blowing in the right direction. Because they have affected the UK in the past. In fact, in about just 1893, there was a huge eruption in Iceland. Yeah. And that actually caused a really, really cold winter and basically produced almost a famine, especially in France. Because there's so much dust in the atmosphere, not enough light could get down, and they didn't grow enough food.
Lovely. Thank you very much indeed.
Thank you, Sue.
Dom in Newmarket, Dr. Dave. And I don't know whether he's asked this question before, but he says, how do transmitters work?
Okay, but I'm guessing he means radio transmitters. Radio waves are a sort of distortion in the electric and magnetic fields of the world. They're called an electromagnetic wave of the universe. Basically, if you get an electric charge and move it, accelerate it up and down or in any direction, it will emit electromagnetic waves. Now, depending on how fast you vibrate the electron or the charged particle, it will affect what frequency of electromagnetic waves you get. So if you vibrate them incredibly fast, like it's sort of the speeds at which electrons are orbiting atoms, you get things like light and infrared light. If you do it quite a lot slower, then you get radio waves. So the way a transmitter works is it causes an electric current to flow up and down a piece of wire, the aerial, and this causes the electric field in the world to change very rapidly, and then that causes sort of ripples to go out in this electric field, and those ripples are radio waves. Your radio in the corner can pick those up and detect them and convert them back into sound, and you can hear them.
Thank you very much indeed. Let's go to our next question right now. Dr. Dave, on the internet, the Russians have a blueprint for a superplane 500 feet of wingspan. Could it be made? And what about the pressure on the centre point of the wingspan structure? And that's coming from Mike. Dave?
I don't. I mean, it depends on everything. The bigger you make a plane, the more difficult it is to take off. I haven't heard of this particular plane specifically, and definitely the longer the wing is, the more difficult it is for it to hold together because there's more leverage on the wing, so it's going to have more force right on that centre, on that wing box, which is holding the two wings on, so it's twisting it. Basically, it will get more difficult the bigger you get. I don't know how practical it is. I do know the biggest, definitely the heaviest planes which have ever been made are things called Aeroplanes or wing and ground effect planes. These will only fly very low and very close to the ground, because when a plane is very close to the ground, it gets extra lift and there's less drag on it. Essentially, when it's very close to the ground, the air can't run away from underneath it, and it sort of piles up and you get extra lift for the same amount of drag. So the Russians did build, I think during the 80s, a plane which was 500 tons, which is significantly bigger than anything else which has been built since. But it would only fly at sort of 20 or 30 feet off the sea. But I don't see any specific reason why it couldn't work, building a plane that big. But I could imagine the practicalities it might get less efficient because you have to have a very, very thick wing to be able to take those huge forces. And it might not necessarily work especially well. I don't know the specific plane you're thinking of, so can't really comment anymore.
Now, let's go to the email. And this has come in from Joel. He says, I'm a musician of sorts, and I just wonder, how can you possibly get so many instruments and layers to a music from a single diaphragm? He's talking about his iPod headphones, I think. How can a single flat piece of plastic produce such a variance of sound all at once? Dave?
That is a very, very good question. Basically, the way your headphones work or a speaker works is as I think you mentioned in your email, you've got a magnet and a coil of wire near the magnet, and that coil of wire is attached to a little diaphragm. You put an electric current through that coil of wire, and that wobbles, that attracts or repels the magnet, and that moves the diaphragm, which moves the air, and moving vibrations in the air are what you hear as sound. Now, essentially, it doesn't have to create the same effect as exactly the same effect as a whole orchestra of instruments around you. All it has to do is create the same effect in your ears. So it's got to do the same thing in your ears as the whole orchestra of instruments. And what gets to your ears is just an air pressure. So the air is just vibrating in and out of your ears, and it just moves your eardrums. So as long as this diaphragm can move your eardrum in the same way as the whole orchestra, then you're going to hear it as the orchestra. And basically it's your ears which do the taking apart all the different sounds, all the different layers, and attributing one to a violin and the other one to an oboe or whatever. And so it's basically the cleverness of your ears. So all that recording does and the loudspeaker does is you have a microphone which measures the air pressure, the movements of the air on it, where it is sitting. And then all you do is you feed those movements back into your headphones, and they create the same movements in your ear, so you'll hear exactly the same thing as the microphone heard. Give or take, roughly.
Our next question comes from Nigel in Willen Park. He says, please ask Dr. Dave if the ice cap will slide seawards on the meltwater, and does the dust affect radar? And does the dust seed the clouds to form rain?
In general, there's no reason why an ice cap couldn't slide seawards if you melted enough under it and it started floating on the water underneath it. I think this particular ice cap is a volcano with a crater in the top of it, and the ice cap is actually sitting in this crater. It's 3 or 4 kilometres across, and the water is just escaping down at once. That small gap in the side of this crater, so it's very unlikely that the whole ice cap is going to start moving because it's trapped inside this crater. So even if it was floating around like an iceberg, it's not going to be able to escape the crater because it wouldn't get through a little gap in the side. Will the dust affect radar? I'm not entirely sure. I'm sure it will affect it. Probably, I don't know if it will affect as much as an equivalent density of cloud. I'm pretty sure you can see it with radar, and it will reduce how well the radar waves will travel. But the particles of the dust are going to be very, very fine, and the way you absorb radar is essentially by causing electric currents to flow in something. And in order to get any decent electric currents, you need something similar to the wavelengths of the radar, and the wavelength of the radar is probably of the order of centimetres, and the particles of dust are going to be sort of hundredths of a millimetre, thousandths of a millimetre. So, especially if they've been up in the air for a long time. So I expect it will absorb radar, but probably not much more than the heavy rain cloud, which is a more similar size to the wavelength of the radar. And there was a third question there.
Yes. Does it seed the clouds to form rain?
I see no reason why it shouldn't. I do know that sometimes in previous volcanic eruptions you get sort of very muddy rain coming down, actually, because the dust has been mixed in with rain. And it will create somewhere for water droplets to form. I see no reason why it shouldn't seed clouds and create rain, yes.
And it's time now to go to the phones, because Sheila, the shepherd, is on the telephone. And you are actually a shepherd, aren't you, Sheila?
I am, yes.
It's lovely having you on the programme. What's your question for Dr. Dave?
My question for Dr. Dave is, I've heard that silverfish are sort of related to dinosaurs and things. And if that's true, like they're prehistoric a bit, should I not keep hoovering them up my hoover and sort of preserve them a little bit more? Or should we just keep killing them off?
Excellent.
I don't think they're related to dinosaurs themselves, but things very like silverfish have been around for a very, very long time. There's certainly been fossils of them sort of 300 million years ago, if not more. But then again, the things related to every creature have been around for that long. I mean, our ancestors, they didn't look very like us, but they were around hundreds of millions of years ago, because we've slowly evolved all from creatures which have been around for billions of years. I mean, the closest things we know related to dinosaurs are actually birds. And so the individual silverfish certainly haven't been around since the dinosaur days, but things which looked a bit like them have. I mean, similarly, there are things which look like jellyfish have been around since long before dinosaurs around, for sort of 500 million years, 500, 600 million years. So I think you can keep on hoovering them up if you like. Lots of insects have been around for that long as well. They've found things a bit like mosquitoes around since the dinosaurs' time, definitely, and spiders since very early dinosaur times.
Okay.
So the question is not really how long they've been around, it's how many of them there are about at the moment, whether you should worry about killing them.
Okay, lovely. I'll keep hoovering them up the hoover. Thank you ever so much. Thanks a lot.
Joy talking to you. Thank you very much. Bye-bye. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Dave has sent an email in, and he says, Hi Sue, we used to hear about and see many pictures from space regarding the depletion of the ozone layer before global warming and climate change. So what has happened to the ozone layer in the last decade or so? Because we haven't heard much about it.
I mean, the ozone layer is still there, luckily, otherwise we'd be all getting horribly sunburnt. The amount of ozone did drop, about halved between 1980 and 1990, so it probably dropped somewhat more at the South Pole even before that. And since about 1990, it's been dropping a bit, but it's sort of levelled out. And that coincides with the time when CFCs were starting to get banned very seriously. And the amount of CFCs which we were releasing had dropped a lot. And so the ozone layer has basically levelling off. And with any luck, it will slowly start getting thicker again as ozone is created by things like lightning and ultraviolet light from the sun. And it hopefully slowly, as the ozone starts getting recreated and the CFCs slowly fall out of the atmosphere or get destroyed, the ozone layer will slowly build up to its original levels. It's actually a remarkable success story for conservation, because there was a problem. Actually, the world did something about it, and it looks like it's going to be all right and it's going to sort itself out. That's why I haven't heard anything about it, because it's essentially a success story.
John, our vintage radio engineer, he asks, the dust from volcanoes, one would think that this would be a good electric insulator, and he would have thought that it wouldn't have had a great effect on radar. Can you explain why? And if it does, how does it affect it?
Yeah, I don't think it's going to affect the radar very much. You're right, it's going to be a pretty good insulator. I think just by having enough stuff in the way, it's probably not... You probably can polarise each piece of dust a little bit, so electrons can move inside each atom a bit, and you can get a charge on one side and charge on the other way. Sort of similar to the way you can charge up an insulating balloon, and that will absorb some energy, but nowhere near as much as something which conducts. And I think you're right, it would probably absorb much less well than water. But then again, if it was mixed with water, it would make the water conduct a lot better. So if you get a rain cloud with a load of dust in it, it will probably absorb microwaves radar a lot better than a rain cloud without the dust in it.
This is from DJ. Hello, DJ. I was walking on a railway platform in a bitterly cold winter day when I stepped beneath a bank of infrared lights. I immediately felt warm. How are these light bulbs designed to produce such large amounts of infrared light? So how do outdoor infrared heaters work?
Infrared light is just a form of light. Its wavelength is a bit longer than red light. In fact, the stuff which you get from infrared light is quite a lot longer than red light. And basically anything which is hot gives it off. You're, in fact, glowing at the moment, Sue.
Thank you.
In the infrared.
Right.
Not especially brightly. And if you get hotter, the sort of bluer the light, the shorter the wavelength gets. So if you once you get up to 600 or 700 degrees centigrade, you start emitting some red light. Up over 1,000, maybe you get sort of yellowy light, and then paler and paler yellow until eventually you get white light. So the trick to make something which produces lots of infrared light is just make something hot, but not too hot. So basically the bulbs on infrared heaters have got a very large filament, which is a lot cooler than a normal filament. So, because it's not hot enough to make, it makes a bit of red light, but it's not hot enough to make yellow, green or blue light. It doesn't produce much visible light. It does produce an awful lot of infrared light, which heats you up nicely without blinding you.
Mike has asked, is it true that the Romans learned that mixing volcanic ash with silica made waterproof cement?
The Romans certainly did have a form of cement. I think basically they were very lucky in that they discovered somewhere on the side of a volcano in Italy, essentially Portland cement. There's some limestone with a bit of silica in there, and it had been cooked by a volcano. And they discovered that if you took this sort of soil basically and mixed it with water, it would set and go very hard. And they were certainly using cement all over the place. I know Bath has got cement in the old Roman baths in Bath, and to make arches and things, because they stuck their bricks together with it to make very, very solid arches. The Pantheon, I think it is, in Rome, has got a huge dome which is made out of concrete basically. And yes, the Romans had cement in concrete, and they used it very effectively.
Yeah, very clever stuff. All right, let's go to another question now. This has come in from Bailey, and I like the idea. I'm glad you're enjoying the show, actually, Bailey. It says, why can't dogs talk?
It depends what you define as talk. Dogs can communicate with their owners and with other dogs and get some idea what they're trying to say across. You know, they'll growl at you if you're doing something they don't like, and lots of pulling their teeth back and looking scary to be aggressive. Which is a very sort of basic form of talking. To speak with a voice in the sophisticated way we do, I think you need some quite major changes to your throat. And babies, very young babies, don't have it. I think they lose it, and they also lose the ability to drink and breathe at the same time. They have to do that in order to be able to speak properly, because the larynx has got to change a lot, and the throat has got to change in order for us to be able to make the wide range of noises which we can. I guess really fundamentally the reason why dogs can't talk and haven't evolved to talk is there hasn't been a good enough reason for them to there hasn't been the pressure to talk.
That's true, yeah, that's true. Cats have staff, don't they? They don't need to talk, so it's a whole thing, yeah.
Whereas at some point in the past, humans has been a very big advantage to be able to talk. The hominids who could talk better have had more children, and so their children were better at talking on average, and slowly people got better and better at talking over millions of years.
Dr. Dave, one on the text here from Malcolm. He says, sorry this is a bit late, but if this cloud of ash is at 20,000 feet, why can't aircraft fly at 10k until they're clear of it, at least those westbound?
I'm guessing they're worried that although most of the ash is at 20,000 feet, some of it might be falling down all the time, and you might get some kind of turbulence which pulls a load of ash down, which your plane then flies through. And also planes are an awful lot less efficient when they're lower down, because there's more air resistance, basically because there's more air. And so if you're trying to fly across the Atlantic, if you've got enough fuel to fly across at 35,000 feet, you won't have enough to fly across at 10,000 feet, so you might find the planes don't actually have enough fuel to get where they're going.
Now, let's go to the email. This is from Alison. What determines where water goes once it's evaporated?
Basically, when water's evaporated, it's a gas. It's water vapour. The molecules are flying around the place, and it behaves just like a gas. So the water molecules they'll diffuse slowly, so because all the molecules in the gas are moving around all the time, bashing into things, and so slowly they'll kind of diffuse out. They'll kind of slowly mix in with the air around them, and so even if the air wasn't moving at all, then the water molecules would move slowly out. but the air is always moving, particularly if you've got a load of water vapour in one place, because water vapour is less dense than normal air. So that air will tend to rise, especially if it's probably warm, if there's a lot of water vapour in it. And so the water vapour will rise with it. And then it'll basically move around like a gas would until it hits something cold. When it hits something cold, it can condense, or if it itself cools down, then the water molecules can bash into each other and start sticking together and form little water droplets. Then you get a cloud. Or if it hits something cold like a mirror, then the water molecules will stick to the mirror and give up some of their energy to the mirror, and they'll cool down and they'll form water droplets on the mirror, and it will condense there. Or they can condense on a cold bit of the wall, and then you can get sort of damp walls, condensation on your walls, and then you grow mould and it goes horrible. So yeah, basically the water vapour will just move around with the air, like air, until it hits something which it will condense on.
Now, Saptarish has sent an email in, and he wants to know, why will sea level rise if the ice caps melt?
It depends where the ice is. If the ice is sitting on top of water and it's floating on water, so the sea ice, then basically a kilo of ice, it's slightly less dense than water, and it's floating, and it's taking up the space of a kilo of water in the water. So if it melts, then it just shrinks a bit and takes up the space it would have taken up by floating, and it won't affect the sea level very much. Global warming will affect the sea level even if there was no ice involved, because the water will get hotter and expand, and that will cause sea level rise even without any ice going on. But the ice melting, which is important, is the ice on land, so especially the Greenland ice cap, the Antarctic ice caps, because if they melt, they're not being sorted by water, and so basically you're just pouring extra water into the sea, and if you pour extra water into the sea will get higher.
Mark is asking, why does cling film balloon over my food in the microwave?
Okay, what's happening when you heat up your food? It's getting hotter. That's going to, if there's any air in the food, if you heat up gases, they expand and get bigger. So if you've got your cling film around it, then it's sealed and the gases are expanding and pushing on the cling film. Also, if you heat up water enough, it will boil and produce water vapour or even steam if it gets over 100 degrees centigrade. And that when water expands to form steam, it expands over 1,000 times, 2,000 times. And so a little tiny bit of water turning into steam will produce an awful lot of expansion and blow up your cling film. Unless it can escape, it's going to keep blowing up until it goes pop.
How does a sailboat sail into the wind? That's an email sent in by Lee.
Very good question, Lee. You often think of a sailing boat working by the wind just pushing on it and acting as drag, and the wind just pushes on it and goes downwind in the direction that the wind is pushing on. But people worked out ways of sailing in a more advanced way than that, in fact, thousands of years ago. What you do is, if you can set your sail up right so it's slightly curved, if you're sailing sort of maybe 45 degrees to the wind, into the wind, you set up the front of the sail so it's pointing into the wind, and then the back of the sail is pointing back towards the back of your boat. So the air gets sort of pushed around a corner as it goes over your sail. And that actually generates lift, and the lift it's generating is at right angles to your sail, which is actually forwards on your boat, so it's sort of maybe 45 degrees to the direction your boat's pointing in. So your boat's getting pushed sideways and forwards a bit, and you have a big fin at the bottom of your boat which stops the boat going sideways, so the boat goes forwards, and because the boat is pointing 45 degrees into the wind, you go into the wind.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.